Hi there and welcome to this video. My name's Warren Toomey and you've probably come across this video because you've done a YouTube search asking the question, how does a CPU work? And maybe this is a question that's been intriguing you for quite a while. Or alternatively, you might have said, well, I sort of have an idea of how a CPU works and maybe I'd like to build one. Well, I'd like to let you know that you've come to the right place. I've just finished designing and building quite a simple CPU that's reasonably easy to put together, and if you watch this video and the other videos in my series, you'll actually be able to see how it works, and it'll help you understand how CPUs work themselves, and you'll even be able to build it yourself and get it to work. But before we go any further, I'll just give you the option that if what you're really after is a coverage of how computers work all the way down to how transistors work, up through the ands and ors and the logic gates, and then progressing up into how CPUs work, then I would highly recommend that you stop watching this video right now and head off to look at Ben Eder's excellent 8-bit video series. He does a great job, a fantastic job actually, of starting all the way down at the transistor level and working you all the way up to create a very simple CPU. On the other hand, if you want to keep watching, what I'm going to give you is a much more high-level component view of how a CPU works. So I'm not going to cover the gates, I'm not going to cover binary, I'm just going to basically say this is what this component does and this is what that component does. If you go with Ben's view of the world, he'll also get you to build a very simple 8-bit CPU spread out over quite a number of breadboards. If you stay watching mine, then the CPU itself is actually slightly smaller, less components, but is actually a little bit more powerful. Both of them are quite easy to build, so either way you'll end up learning a lot about how CPUs work, and you should be able to build one of them yourself. Well, it looks like you're staying here to watch this video, which is excellent. You still should go and check Ben's videos out at some point. So let's have a look at the CPU that I've designed and built. It's called the Crazy Small CPU, and I've actually made some slight changes to it, so we're up to version 2. In terms of chips, you only need about 11 chips for the CPU itself and a couple of extra chips to do output, so you can plug it into another computer and get it to print out stuff. If you've done any breadboard work beforehand, it will fit on 3 breadboards, and it's reasonably easy to build. Now I'm going to give you the lowdown that before I built this, I'd actually never done any breadboard work. I'd never done any digital logic design or implementation. So the fact that someone who knows pretty much nothing about how to put chips on a board and wire them up can actually get to build this means that it's probably actually quite easy to build. Now, in terms of what sort of power you're going to get out of this, well, it's not going to be any sort of i7 or AMD chip or anything like that. You're going to have 256 instructions in your ROM memory. You'll be able to access 256 RAM locations in your RAM memory. You will be able to output characters out to a screen, so ASCII characters. And it comes with an assembler, so if you want to learn how to do assembly language, you'll be able to program the CPU and assembly code. If you don't really want to put the breadboard version together, there are 2 simulated versions of the CPU so that you can actually do it all in a Linux box, write assembly language, assemble it, and then run it without actually having to build the breadboard version. And if you want to actually just look at a high-level language, then I've got a sort of a really cut-down version of C that you can compile down to the assembly version, and then you can run it in the simulator, or you can run it, of course, on the breadboard version that you're going to build. And of course, I know you're going to build it because it's reasonably simple and it's a great benefit. You can actually say you've built your own computer. Now, why did I call it the Crazy Small CPU? Well, I'd watched Ben Eder's video series, and while they're excellent, you end up with this something like about 10 or 12 breadboard version of a computer, and there's more than 2,000 chips in there. And I thought, well, there's got to be a way of doing a similar sort of a CPU, but with a minimal number of actual chips. And so I've been able to get it down to around about a dozen chips. Now you might think, well, okay, if you've cut down on the number of chips, surely it actually must be less powerful than the one that Ben Eder designed. Well, it's actually quite powerful, and you could probably say it's even more powerful. It's got more instructions and it's got more memory locations. What I've been able to do, I've been able to calculate all the Fibonacci numbers up to something like 27 decimal places. The CPU can actually print out a sine wave, calculate and print out a sine wave. And if you know anything about the Tower 7i, it will do, I think, 9 disks and tell you which moves to make for all of the 9 disks to get the tower from the left-hand side over to the right-hand side. So it's actually quite a powerful little device. If you want to look at the high-level language, as I said, it's a cut-down version of C. You've got variables, you've got assignments, expressions, you've got if statements and while statements. You can break out of loops. You've got the plus operator. And you can actually break your program up into multiple functions, and functions can call other functions. And all of that will get compiled down to the assembly language, which will then get converted into the binary, which you put onto the ROMs, and then you can run the ROMs on the breadboard, and the output will come out and be displayed on a computer screen for you. Alright, so I'm going to use this crazy small CPU as the vehicle in this video to describe how CPUs actually work. But before I get to that, I just need to cover a couple of other things. Now, I'm going to try to avoid talking about binary. I'm not going to talk about arithmetic. I'm not going to talk about buses and bus widths and things like that. But I do need to talk about 2 different types of components that we're going to have in our design. And the first type of component is known as a combinatorial component. Now, what that means in terms of digital logic design is that the component takes a bunch of inputs, so a bunch of zeros and ones that come from somewhere else, and based on what those input values are, it does some sort of calculation or maybe lookup if it's a ROM, and it produces outputs. And the output is purely a function of those inputs. And what that means is, as soon as the inputs change, then the combinatorial component will do something and produce the output that corresponds to that input. Okay, so there's no time delay. Well, there is obviously, because electricity takes a while to move and we've got other causes of latency, but generally as soon as the input changes, then the output will change right away. Now, in terms of the design that's coming up, we've got an arithmetic logic unit that acts as a combinatorial component. You give it inputs, you tell it what operation to perform, and it spits out the correct outputs. We'll also have a ROM, 2 ROMs, actually 3 ROMs, and you apply a particular address on the ROM, and it goes into its storage of information, and it looks up the information at that location, and it produces that on its output. And finally, we'll see a multiplexer, whose job is to actually make a choice between 2 inputs and choose one of those inputs and direct it as its output. Now, apart from combinatorial components, there's another type of component that we need to look at, and they are sequential components. Now, a sequential component is something that holds state. And what that means is that it was given an input in the past, and it will keep a memory of that previous input. And while it's keeping that memory, that's going to be its output. So, for example, in this diagram on the bottom right, if the input was previously the number 7, we would have kept a copy of that number 7, and until something happens, we'll keep spitting the number 7 out on our output. Now, later on, the input might change to be the number 10. Now, until something happens, we will keep spitting out the number 7, which is what we've stored as our state internally. So number 7 is being output, even though the input is number 10. Now, how do we actually get the input to be accepted and to replace the state in the sequential component? Well, we need 2 things. Well, at least 1 thing, but maybe 2 things. We need a clock pulse, and we need the clock pulse to go from low to high to tell the component that now's the time to look at your input and make a decision about what to do with it. And most sequential components also have some sort of a load signal which tells them yes to accept this new input, or no, even though the clock pulse has gone up, to still ignore that input and hold on to your existing state. So for most of our components, we'll expect to have a clock pulse to tell it when to accept the input, and we'll also have a load signal that says yes, now's the time to actually load that value. And once a new value is loaded internally, it immediately gets placed on the output. Okay, so just to summarize, inputs and outputs might differ because we might not be accepting the input right at the moment, and in fact we have to wait for the clock pulse anyway. And how do you know that a sequential component is a sequential component? Well, I'll always indicate that by a little triangle at the bottom to say we are waiting for a clock pulse to come in high to decide whether or not to take the input in. In terms of the design that's coming up, we'll have registers that store just a single number, and they're sequential. And we'll also have a RAM chip which can hold up to 256 different pieces of information. And again, we can change the value of what's in RAM, but only when there's a rising clock pulse. All right, now we're up to the actual architecture. And this diagram looks pretty complicated, and so I'll hopefully be able to go through it and explain how each of the components work. You should also realize that this is only what we call the data path of the architecture. So these black lines are just showing you how data is flowing through the CPU. So let's start up the top, and in fact the top half of this diagram is all about the data, calculating information and storing it and loading it back again. And the bottom half of the picture is all about how do we control the things in the top half of the diagram. So I'm going to start up in the top right with the arithmetic logic unit. So the purpose of the ALU is to do calculations, and really it's essentially the heart of the CPU. So we can do things like add and subtract. In more powerful CPUs, we'd be able to do multiply and divide. For those people who know a bit of binary, we can do things like ands and ors and exclusive ors. So it's the thing that does the processing of the data. And typically it operates on two pieces of data. So we've got two pieces of data coming in, and we'll send in a control that says, okay, now's the time to do addition. And because this is a combinatorial component, the output of the addition happens immediately, and it's going to travel down this line, which we're going to call the data bus. The ALU will also spit out some information about what type of result comes out, whether it's negative or zero, and we're going to call those the flags values. Now, most of the time you want to have information, and lots of information, so we're going to need to store that over here on the left in the RAM, the random access memory. But of course, the only problem with the RAM is that it's connected with a single data bus, a single set of lines. And so if we want to actually get one number out of RAM and make it the input to the ALU, and then get a different number out of RAM and make it the second input to do addition, well, we can't do that because we've only got a single data bus. So what we do instead is we actually have temporary storage. We call these things registers. So a register is a sequential circuit whose job is to load information from RAM and hold on to it so that we can go back to RAM and get more information. So you can see that we've got two registers, the A and the B register. And what we'll typically do is load something out of RAM, bring it through the multiplexer, which I'll tell you about in just a minute, store it in the A register, and then turn off its load line so that it'll hold on to that state. Then we can go back to RAM, get some more information, bring it into the B register while the A register is still holding on to the previous information. And now when both of these are loaded up with information, we tell the ALU to do a certain operation like subtraction, and then of course we can write the result of the ALU down the data bus and store it into memory in a third location. And that's effectively what the CPU is doing all the time. It's getting information from somewhere, it's putting it into registers, it's making an operation on that information and possibly putting it back out to RAM. Now sometimes you actually don't want to load stuff from RAM, so maybe you already have in your program knowledge of something you want to do, like you might want to add the number 2 to something, and the number 2 might not already be stored in RAM. So another place to get information is from the instructions. So in the ROMs down the bottom, we're going to store our program. And one of these ROMs is going to be the address ROM. And the job of the address ROM is to tell which location in memory we want to load from, or which location in memory we want to write back to. But there's a third, well, in fact there's a third and fourth thing that it can do. And the third thing that it can do is we can actually use the address as actually a constant number. So we might want to load the number 2 into the A register. So we'll put address 2 here. We're not going to use this address for accessing memory, but we're going to take that number 2 and bring it up through the bottom half of the multiplexer, and we're going to take that number 2 and store that in the A register. So we can use the address for addressing locations in memory. We can use an address for actually being a constant, and we can load that constant through the multiplexer into the A register. So that means now we need to cover the multiplexer. The job of the multiplexer is to make a decision as to where we're going to get information to place into these registers. And so we have a control line coming in to say either take information off the data bus. So in other words, we might even actually be doing a calculation from the ALU. We might even do A plus B, and we want to store that back in the A register. So we've got A plus B outputs, do an addition, send it down the data bus, and bring it through the multiplexer and store it back into the A register. So the multiplexer makes a choice. Do we want to load the registers from something that's on the data bus? Could be the ALU output, or could be the RAM output. Or alternatively, do we want to load a constant value out of the address and put that into one of the registers? Okay, so it's a bit like a gate. It can choose to either select information from one direction, or to flip the gate over and choose information to come from a different direction. Alright, so that's the top half of the CPU done, and that's pretty much the thing that does all of the work with the data. So let's move down to the control section. Okay, we've got our clock, and it's going to be producing pulses going up, going up, going up, going up, and every time we have a clock pulse, something might happen with our sequential circuits, A, B register, the RAM, and the program counter. The job of the program counter is to choose which next instruction we're going to perform. And we'll start with the program counter at 0, and then we'll look up the instruction in the ROMs at location 0, and they will go out and do the job of controlling the data section. And once we've done that instruction, the clock pulse will go down, and then it'll go back up again, and we'll have incremented the program counter. So every time we get a clock pulse, we move up to the next counter value, 0, 1, 2, 3, 4, etc., etc., etc. And then once we've moved to the next instruction position, that will look up in the ROMs what instruction to perform, and they will then send out the control lines and the address values to go and control the data section. So the ROMs are doing the job of providing the address in RAM or the constant to go and do things onto. And the control ROM's job is to actually send out control signals that will control the ALU. What additional subtraction should we be performing? Are we going to be loading the B register? Are we going to be loading the A register? Are we going to choose from the data bus or a constant? And are we going to read from memory, or are we going to be writing to memory? So we've got a whole bunch of things that have to be done by the control ROM for each and every instruction. And finally, the flags register. Now, as I said before, the ALU, once it does a calculation, this calculation might be negative, might be 0, it might be too big to fit back into RAM, so we have what's known as a carry. So that information about NZ, overflow and carry, there's 4 flag values, gets stored in the flag register. And when we want to make a decision about what instruction to do next, well, we can look at the flags value, because they also feed into the ROMs as well as the program counter. So we might say that when we get to instruction 5, if there's been a carry because the information that we calculated was too big to fit into memory, then instead of going to instruction program counter number 6, we will actually tell the program counter to jump. And what that will mean is that instead of going to the number 6 from 5, we'll actually load the next address into the program counter. And so we might jump to instruction 10 instead of doing instruction 6 next. Okay, so that means the address values are not only RAM addresses and constant values that can be loaded into registers, but they can also be the next program counter value for when we're doing jumps. So we might go 1, 2, 3, 4, 5, 6, and then the control lines say, okay, now's the time to jump because we've had a carry, So address, please load yourself, and program counter, please load the number on the address bus and jump to program counter number 10. Okay, so that's basically how a CPU works. We've got something that does operations, we've got temporary storage of information in registers, we've got RAM to write to and read from, we might want to load from RAM, we might want to load constants, and down in the bottom half we've got something that chooses where the next instruction is going to come from, its position 0, 1, 2, 3, 4, 5, and once we look up that instruction we send out the addresses and the control lines that control the data components in the top half of the CPU. And that's basically how CPUs work. Now, they do this millions and millions and millions of instructions in every second, so they seem to be doing an awful lot, but what they're actually doing is an awful lot of dumb things every second. So now that you've seen the data side of the CPU and got a glimmer of how the control is actually happening, let's actually color in those control lines. Alright, now it looks much more messy. But what you can see is pretty much every component has some sort of thing that we have to control. So for example, with the A register, apart from the clock, do we load at this instruction something into the A register, or do we turn this off and leave it with its original state? Do we load something into the B register, or do we just leave it in its original state? Are we writing out to RAM? So in other words, are we writing in the direction of ALU into RAM? Or when this is turned off, are we actually reading from memory, and in which case it's going to be going into the multiplexer? And of course, when it goes into the multiplexer, are we choosing to load from the data bus side of the multiplexer, or if we turn this on the other way, are we actually loading a constant and we're getting that from the address ROM? So we've got a lot of lines: RAM write, ACell, A load, B load. When we do an ALU operation, as well as writing out to the RAM, we're also going to take a copy of the 4 NZVC flags, and of course, so therefore the flags register has to also be told about the RAM write operation. The ALU, of course, has to be told what arithmetic or logic instruction to perform. So we've got a bunch of lines coming in that will choose one of 16 operations to perform. Now when we're doing addition and subtraction, as I said previously, our result might not fit into the storage. So what we'll do is, just like you do when you're doing long addition on a piece of paper, you'll do one column, and if there's a carry, you'll float the number 1 over to the next column to the left, and you'll add that as part of the next operation. So when we've had a previous carry, that will be stored down in the flags register, and if we move up to a left-hand column, we'll be able to suck that carry in and know that we've got to add an extra 1 in the next column when we're doing the next column's worth of addition. All right, and one more load line, whether or not we should increment the PC, or whether we should load when we're doing a jump and load its value from the address. All right, I think I've probably made your brains hurt too much in this one video. That's enough to explain how basic CPUs work. I certainly am not covering things like caches and predictive branch instructions and pipelines and all of that sort of stuff. This is just enough to get the most elementary ideas about how CPUs work. I've got a follow-up video to this coming up on number 2, and in number 2 I'll actually go through the crazy small CPU architecture in a little bit more detail, explain what the instructions look like, and talk about 2D operations, which is quite interesting. But for now, hopefully that's been interesting, and if you do find this interesting, then hopefully you'll keep watching the rest of the Crazy Small CPU video series. Alright, I'm Warren Toomey, and I'll say goodbye for now.